We're now ready to start to implement breadth first search, and we're going to write some code to actually implement the algorithm. We're going to see how that queue that we just talked about gets incorporated in. We're going to do this in Python-like code. It's going to be pseudo code just so you can get a sense of the algorithm, and it should be relatively easy to translate that into Python once you're ready to do that. Let me first remind you how breadth first search works. I give you a graph, I give you a start vertex, I give you an end vertex, and your job is to find the shortest path, which may or may not be unique, between those two vertices. That is, how do I move along edges between vertices in the shortest number of hops between these start and end vertices. And the way breadth first search works, I start at the start vertex, I take one step out to every vertex that is adjacent to me. I label all of those as having a distance of 1 with a back pointer to me. For each of those, I take another step out in 1 for each adjacent vertex that has not previously been visited. Those vertices now have a length 2 with a back pointer to the previous one, which back points to the start vertex, and we go again and again. So there's essentially a moving front of length 1, 2, 3, 4, and eventually I will find the vertex that I'm looking for if it is connected to me, and I will, by definition, have a shortest path. Okay, so let's now write the code to implement that. So we're going to start by initializing a queue with the start vertex, and we're going to set the distance of that start vertex to 0. It may not be obvious why you need that queue, but you'll see it right now. So let's see. So here's my initializing of the queue. I'm going to set the distance to 0. So S is going to be the start queue, the start vertex. Now, while the queue is not empty, pop the queue. So I'll use the term delete here instead of pop. I don't know why I switched that. So X is now the first vertex that was inserted into the queue. And for each vertex Y that is adjacent to X, do something. Okay, I'll fill that in a minute. So first of all, let's look at this. How do I determine adjacency? Well, that depends on the representation. If I have an adjacency matrix, I find X in the adjacency matrix, and I simply walk along a single row or a column, and I ask, are you adjacent, are you adjacent, are you adjacent? Is there a 1 in that representation? If there is, well then Y will be part of that, of this loop. Now, if Y has not been visited, so if Y has been visited, how do I know if it's been visited? Well, we'll have to deal with that in a little bit. But if it's not been visited, I have some work to do. What's the work? Well, I'm going to set the distance to that vertex to be 1 plus whatever the current distance is. I'm going to set the back pointer to that to be X because I just went from X to Y. And then I have to have a promise that I'm going to visit Y's neighbor eventually. So that's where the queue is going to come into play. So let's look at it. Y's distance is going to be X's distance plus 1, right? So X has a distance because it is set to 0 here. So I'm going to increment its distance to 1, and I'm going to set its back pointer to X. Of course, I just got from X to Y. And here it comes. I'm going to push or insert this vertex into the queue. Okay? So let's see how, so that's it. That's breadth first search. A couple of details when you actually go to write this in Python, the adjacency matrix and all that, but that's okay. This is pretty easy. Now let's make sure we understand it conceptually. So here's my graph. My start vertex is D. So this is going to be my queue right here, and this is going to be where I store that information about the distance for all of the vertices and the back pointers. So this is just a simple list where I store 3 pieces of information: the name of the vertex, the distance, and the back pointer. So initially, I put the start vertex on the queue. I set that distances to 0, and of course it doesn't have a back pointer because that is the start vertex. Okay, so now I'm ready to go. So we're going to pop that D from the queue, and then for each vertex Y that is adjacent to it, I'm going to do some work. All right, so let's go ahead and pop it. Who's adjacent? Well, let's see. I, B, and G is adjacent to D. That is, it's connected by an edge directly. So for each vertex Y, so Y is going to be I, B, and G. If Y has not been visited, well, how do I know if it's been visited? Well, I just look it up in this little table here. So I just filled this in here, but it wasn't previously, it was previously empty. B was empty, and of course, G was empty. So that's how I tell if I've been visited. If I have a distance or a back pointer, well, then somebody has already visited that vertex. So I'm going to set the distance to be X's distance plus 1, so I add 1 to it. And my back pointer is going to be whatever X was, which is D. So that's the I right there. And look what I'm going to do now. I'm going to put y into the node I into the Q. Why? Well, because once I started with this node, I visit everybody who's adjacent to me, and then it's done. But then from each of these vertices, I have to visit their nodes. So it's a promise to come back and do this. All right, so now we do that for B. B gets pushed onto the Q. B gets indexed by 1, same back pointer. So now I have 2 vertices that I have to visit. Same thing for G. G gets pushed onto the Q. G has a distance of 1, back pointer to the D. Okay, so we have now finished the first cycle through here. We've gone through all the vertices that were adjacent to D. We've added them to the table with a distance of 1 and a back pointer to D. And now look at my Q. I have 3 items on the Q. All 3 of these have to be pushed out one more step. Yeah? But let's see what happens now. Now you're going to start to see the power of the Q here. So we come back up to here. The Q is not empty, so I'm going to pop from the Q. So X is going to be equal to I. For each vertex Y that is adjacent to X, all right, so here we go. We've got C, H, B, and D. Let's agree that B and D have been visited before. How do I know that? Because B and D have been visited before, but C and H have not. So we're going to set C's distance to be I's distance plus 1. So that's going to put in, oops, sorry, I guess I did H first. So the order, by the way, just depends on which of these vertices you touch first in figuring out adjacency. So it looks like I did H first. So distance is 2, back pointer is I, and here it is, I put H onto the Q. So look at what's on the Q now. Now you really see why first in, first out is important. B and G were from the first wave. Yeah, I, B, G were in the first wave. We popped I, B and G is still in the first wave. H is part of the second wave. But I shouldn't step past H until I'm done with B and G, but I won't, because the first wave was inserted into the Q before the second wave. So I'm going to pop this and this, everybody from the first wave, before I pop this and anybody else. So here now you see why the Q is in place, is because when I follow I have to have a promise to come back to B and to G, and so I use a Q to make sure that first in, first out. Okay, so H is on the Q. We're done with that. Let's now do the next one. So we are going to, sorry, where are we? Oh, yeah. So H was adjacent, so now C is adjacent. So that has a distance of 2 and a back pointer to I, and those are the only 2 adjacent that have not previously been visited. We are now done with I. So we have finished the first vertex in the first wave. We have 2 vertices in the second wave, but I can't visit those yet until I finish the first wave, which are B and G. So I'm going to pop B. Who is adjacent to B? I, D, G, F, and E. So only E and F are not previously visited, so let's go ahead and update those. So F gets a back pointer of 2, not 3. We're still on the first wave because B's distance is 1, so its distance is 2, back pointer is B. E, of course, is a distance of 2, back pointer is B, and now I'm done with B. All right, who's next is G. So we pop G. That is the last vertex in the first wave. Adjacent to G is B and D. Both B and D have been visited. Nothing to do here. G is of no use to me whatsoever. So notice now I've got a bunch of vertices that are all part of now the second wave. So now, and again, the order here is arbitrary. It really just depended on what order came out of this for loop, and that simply has to do with how you decide adjacency and what the underlying data structure is. All right, so H comes off. Everybody adjacent to H has already been visited, so there is nothing to do. C comes off. I is adjacent, is been visited, but good, A has not. So A, we're going to do a little bit of work. Its length, of course, is going to be 3. Back pointer is C. And now all we have to do is pop F. Everybody adjacent has been visited. Pop E. Everybody adjacent has been visited. Pop A. Everybody adjacent has been visited. And now the Q is empty, and we are done. Okay. And so now, notice, by the way, when I started this, I didn't actually specify the stop vertex. I've actually computed the shortest path to every vertex. So it's a little bonus. But now I can figure out what the shortest path to A is, which is D, I, C, A. Of course, it could have also been D, B, E, A, just depending on the order. But now you simply have to start at the last path, start at the end vertex. What is the length of the path 3? What is the path? Go to C, go to I, go to D, and then you are done. So in this little data structure here, I get the length of the path and I get the actual path. Okay, so that's it. Breadth first search. We need the queue to keep track of the vertices as we are pushing out waves. We, of course, need a representation for the graph. That can be an adjacency matrix or adjacency list, and relatively tight and relatively easy to implement. Okay, last word on graphs is the graph, remember, represents relationships between vertices. And you can have all kinds of edges. This vertex can connect to anybody, including itself. And it's a nice way of representing things like maps, relationships. This, in fact, underlies most of what happens at Facebook on a day-to-day basis in terms of understanding the connectivity of the users. There's one more data structure that we're not going to talk about, but I just want to mention very briefly because it's a really important data structure in computer science, which is trees. And trees also represent the relationship between data, but it represents it in a so-called parent-child relationship. So trees have a hierarchical ordering. If you flip this upside down, you can think of it as a tree. So this is the root, and then we're branching out here. So here we have a parent C that has 2 children, A and I. I has 2 children, B and D. B has 2 children, F and G. So here you can think about this as a familial representation, the way you would see, for example, a family tree. There is no vertices that go backwards. In a tree, everything goes downward. So the difference between a graph and a tree is I cannot, for example, have a connection between B and I, or B and C, or even across. There's this very natural parent-child relationship. And these are really, really useful relationships in all kinds of things. And there's lots of really interesting data structures and algorithms that apply on it. We don't have time in this class to talk about it, but I simply wanted to mention it because it's clearly related to a graph in the sense that it's describing relationship between things, but only a parent-child relationship. Okay, that's it for graphs. There's lots of other interesting things we can do. We could spend literally an entire class talking about graph algorithms. I really just wanted to show you what this basic data structure is, how you represented it, and at least one algorithm on it. So next, we're going to do a little bit more on data structures, and then we're going to transition into the second half of this course, which is the data analytics part. All right, we'll see you in a few minutes when we come back to the next lecture.